In this video, I'm going to show you how to calculate the inverse of a 2x2 matrix. Before we get into the calculations, what even is an inverse matrix? Well, we've got a definition right here. The inverse of a matrix A is another matrix, A to the power of -1, meaning A inverse, such that both A times A inverse is the identity matrix, and also A inverse times A is the identity matrix. This is really just an extension of an idea from arithmetic. In arithmetic, we start with a number, say 2, and we define the inverse of that number, 2 inverse, as the number such that 2 times 2 inverse equals 1, and 2 inverse times 2 equals 1. In arithmetic, the way to compute an inverse is really easy. 2 inverse is just 1 divided by 2, a half, because 2 times a half equals 1, and a half times 2 equals 1. With matrices, however, things get a little bit more involved. But there is a nice formula for the inverse of a 2x2 matrix, which is given here. The inverse of a matrix A consisting of entries A, B, C, and D is given by A inverse is equal to 1 divided by the determinant of A times the matrix which has the entries rearranged a little bit. So this time A and D are switched, so you switch the diagonal, D goes where A goes where D goes, and then you put negatives on B and C. So A inverse is 1 over the determinant times the matrix which has A and D switched and B and C made negative. Let's do some examples to see this formula in action. Here's a matrix A, 4, 3, 1, 2, and we want to calculate A inverse for this matrix. We're just going to use our inverse formula that we went over previously. We're just going to take this information about A and plug it into the formula. So let's go ahead and do this. 1 over the determinant. Well, the determinant of A is just the product of this diagonal, 4 times 2, which is 8, then minus the product of the other diagonal, 1 times 3, which is 3. And then we're going to switch around the entries a little bit. A and D get switched. D goes where A was originally, so 2 goes up there where 4 was, and then 4 goes down there where 2 was, and then B and C turn into their negatives, so we put negative signs on this 3 and this 1. Alright, so we can simplify this a bit. 8 minus 3, that's just 5, so 1/5 of this matrix 2, -3, -1, 4, and if you want to get rid of the 1/5 in front, you can distribute to all the terms, and you'll just get 2/5, -3/5, -1/5, and 4/5. And there you go. That is your inverse matrix. That's the inverse of A. Now let's verify that A inverse satisfies the definition of the inverse matrix. Remember, the definition of the inverse matrix is just that when we multiply A by A inverse, we need to have a result of I, the identity matrix. And that has to be true no matter what side we multiply on A. It has to be true if we multiply by A inverse on the right or on the left. Either way, it has to come out to the identity matrix. So let's just verify this by plugging in our two matrices for A and A inverse. And we'll just multiply them and it should come out to the identity. So A is just 4, 3, 1, 2, so I'll write that here, 4, 3, 1, 2, and then A inverse is just, let's use the 1/5 in front of the whole number matrix, that way it'll be easier to compute. That's just 1/5 times 2, -3, -1, and 4. And we want to make sure that the result of that multiplication is the identity matrix, which just consists of 1s on the diagonal and 0s elsewhere. To simplify things a bit, let's move this 1/5 out in front. So we'll scratch it out here and move it out in front of the whole product. That way we don't have to worry about it until the end. We'll just multiply these whole number matrices first and then apply the 1/5. And when we do that, we get 1/5 times the matrix multiplication, top row times left column, that's 4 times 2 is 8, then 3 times -1 is -3, so 8 minus 3, and then top row times right column, that's 4 times -3, which is -12, 12, then 3 times 4 is positive 12. And then bottom row times left column is 1 times 2 is 2, and then 2 times negative 1 is negative 2. Then bottom row times right column is 1 times negative 3 is negative 3, and then 2 times 4 is 8, so negative 3 plus 8. And let's hope that it comes out to the identity matrix. Otherwise, if it doesn't, then we know we did something wrong in our computations. But this looks pretty good. This is 1/5, and then 8 minus 3 is 5, and negative 12 plus 12 comes out to 0. 2 minus 2 also comes out to 0. Negative 3 plus 8 comes out to 5. So it's looking pretty good. Is this the identity matrix? Well, 5 times a fifth is just 1. So 1's on the diagonal. And then 0 times a fifth is just 0. So 0 is elsewhere. So yeah, this works out. Alright, so we've verified the first condition here, and we can verify the second condition in the same way. We can just plug in for A inverse and A and compute, and that should come out to I. But there is a faster way. Now that we've already done that process and we know that the first condition is true, there's a way that we can use this first condition to verify the second condition without having to go through all the computations. The way we're going to do this is we're going to start by writing this first condition again. Now we know it's true for sure, so we can write it down and use that as a starting point to try and reach the second condition. So A times A inverse is equal to the identity matrix. Now let's multiply both sides of this equation on the right by the matrix A. So times A on the right here and times A on the right here. Now let's write down the equation again, but this time we'll simplify the right-hand side. So we'll keep the left-hand side the same. Just write A times A inverse times A is equal to our left-hand side. But now on the left-hand side, well, the identity matrix times any other matrix is just the other matrix, because the identity matrix just keeps the other matrix the same. So I times A is just A. And now since matrix multiplication is associative, we can put some parentheses around this left-hand side. So this is just saying compute A inverse A and then do A times the result and you'll get A. But if A times a matrix is just itself A, then that matrix has to be the identity matrix. So A inverse A has to be the identity. And that's exactly what we wanted to show. A inverse A is the identity. Here's another example of computing an inverse matrix. So now we've got this matrix here. We want to compute the inverse. Again, we're just going to use the same formula. So 1 over the determinant of A, and determinant of A is just 2 times 3, which is 6, and then minus negative 1 times negative 6, so minus 6, and then, oh, wait a second. This is 1 over 6 minus 6, and we'll have our entries in the matrix here, but that'll come out to 1 over 0 times a matrix. So what does this mean? 1 over 0? Does that even make sense here? Well, no. Anything divided by 0 is undefined. So our inverse is just undefined. Which really just means that this matrix A doesn't have an inverse. In other words, A is non-invertible. To gain some intuition for what it means for the matrix A to be non-invertible, we can compare that singular matrix A to the number 0. As we know, 0 doesn't have an inverse because there's no number x such that 0 times x is 1. 0 times any number x is just 0, and 0 is not equal to 1. So 0 just doesn't have an inverse. Similarly, the matrix A just doesn't have an inverse. There's no matrix A inverse such that A times A inverse equals I, the identity. No such A inverse exists. In general, For the inverse of a matrix to exist, there are two conditions that must be met. First of all, the matrix has to have a determinant. The determinant has to be defined for this matrix. Second of all, the determinant can't come out to 0 because in the formula for the inverse matrix, we're dividing by the determinant. So if the determinant comes out to 0, then the formula just becomes undefined. As a result, there are two types of non-invertible matrices. There's non-square matrices because these matrices don't have a well-defined determinant. If you try to take the determinant of a matrix like 1, 2, 3, 4, 5, 6, well, you're not going to get anywhere because this isn't a square matrix. And determinants are only defined on square matrices. We could take the determinant of 1, 2, 3, 4, or continue this and make it 1, 2, 3, 4, 5, 6, 7, 8, 9, because that's a 2 by 2 and this is a 3 by 3. But if the dimensions don't match up, this is a 2 by 3, then you can't take the determinant. So this formula doesn't even make sense because we can't compute the determinant. Alright, second of all, square matrices whose determinant is 0. For square matrices, the determinant is defined, but if the determinant comes out to 0, then we get 1 over 0 in the formula. To distinguish between these two cases, square matrices whose determinant is 0 are also called singular matrices. So if you're ever told that a matrix is a singular matrix, then you know it's a square matrix, but it doesn't have an inverse because its determinant is 0. Lastly, let's verify this formula that we've been using to compute the inverse of a matrix. Let's show that whenever this formula is defined, that the result satisfies the property of the inverse, that A inverse times A equals I. There's also the case of A times A inverse equals I, but it follows pretty much the same way as this one, so we'll just do this one here. So okay, let's compute this. So 1 over determinant of A. Determinant of A is just A times D, so 1 over A times D minus B times C, so minus B times C, and then let's multiply these matrices. So we've got first row, first column, dA, and then plus negative b times c, so minus bc, and then first row, second column, db, plus negative b times d, so minus b times d, and then next we've got second row, first column, so negative c times a, so negative ca, and then a times c, so plus ac, and then lastly second row, second column, negative c times b, so negative cb, and then plus a times d. And we want to show that's equal to the identity matrix. So let's go ahead and simplify this a bit. 1 over AD minus BC, and here we can write this first entry as AD minus BC, and then here DB minus BD, well DB is really just BD, so these are two terms of the same, but this one's negative, so these cancel out and we've just got a 0. It's the same idea here. This is just negative AC plus AC, which is 0. And then here we can write this as AD minus BC. Just rearranging a bit. And we want to show that's equal to the identity. Well, we're dividing by AD minus BC, and both of these entries are AD minus BC. So yeah, it's just 1, 0, 0, 1. Awesome. There it is, the identity. In the future, we'll see some applications of the inverse matrix, such as in solving systems of linear equations.